Hello, and welcome to Astronomy 100. In the previous segment, we talked about how Wien's law is a very critical tool when it comes to being able to determine the temperature of a body that is too far away from us for us to have the traditional means of determining temperature. And we want to do one final concluding idea related to this. So let's go back to our screen here. What you saw from last time is that it was Wilhelm Wien who discovered that as an object's temperature changes, the black body curve of that object also is going to shift. And the critical thing, of course, to remember is that the peak of the black body curve shifts to shorter and shorter wavelengths as the temperature of the object increases. So an object that is cool in temperature has a peak of its black body curve at a longer wavelength, and then of course the higher the temperature, the shorter and shorter wavelength the black body curve will shift to. And this of course leads us to the formula that we call Wien's law, and we have the version of it that we use in astronomy. And so what we end up with is the ability to determine the temperature of an object based on the light that it's producing. If we can measure the light that it's producing, determine lambda max, we can calculate the temperature of the object. Now, how does this relate to the stars themselves? So let me show you an important example of this. In this picture that you see right here, you'll notice that there's a variety of stars of different colors. Most of the stars appear white. Some of them have an obvious red tint to them. Some of them are obviously blue, and one of them in this case happens to be kind of yellow. So why do stars have different colors? Well, again, it's Wien's law. Let me show you an example. If we were to look at the black body curve for this star right here, take its light, pass it through a prism, spread out its light based on its colors, and what we end up getting is the black body curve that you see here. And you can see that the temperature of this star is 4,200 kelvins. We know that because its peak of its black body curve is here, and when you use Wien's law, we end up with the temperature of 4,200. But what I want you to notice is how this star produces the majority of its light. The brightness of this star is mostly in the red, whereas the light that we see, that is the violet portion of the light coming from the star, is not very bright. So lots and lots of red, not so much violet. Now your eye takes in every one of these colors, but your brain has to show you one representative color based on what's going into your eye. And so your brain is going to show you a color that looks reddish or on the red side because your brain knows that it's getting more red than violet, and so therefore the star will have a reddish tint to it because the majority of the light is in the red part of the spectrum. Now, on the other hand, this star here that has a very bluish look to its appearance, the reason why it looks blue is because the temperature of this star is 7,200 kelvins, and its black body curve is right here. The peak of its black body curve is over the violet. So what you'll notice is that this star produces a lot of violet light, but not as much red, almost a 2-to-1, twice as much violet compared to red. So again, your brain has to show you one representative color based on the light that is getting through your eyes. And so the color that your brain shows you is on the bluish side of things. So a star that looks blue is a star that is hotter than a star that looks red. And this might actually surprise you because in the world around us, we tend to signify temperature in an opposite way. For instance, you might see a sign that warns you of fire or the danger of something very hot, and it will use the color red to indicate something that is hot. Whereas blues tend to be the color that we associate with things that are cool, such as water or various things that are cool like water. But if you think about it, water is not really blue, water is clear, and so we tend to have this misunderstanding about the true nature of color related to temperature that we represent in a way that is backwards. So what you need to do is you need to essentially get rid of the notion that red means hot and blue means cool. When it comes to the reality of our universe, objects that are blue are much hotter than objects that are red. So a star that appears blue is very hot, a star that appears red is very cool, and stars that appear white are actually stars that are in between. So this star right here is hotter than this star, but is cooler than this star. So a star that appears white is somewhere in the middle, because when your brain gets every color of the rainbow all together in roughly equal quantities, your brain is going to show you white. So remember, the colors of stars are one way to get an indicator of the relative temperature of the star. If you want to know the exact number, of course you have to take the information and use Wien's law. But on its surface, Wien's law can help you understand the temperature of an object just simply by the color that that object is producing. The next part is, how do we determine what something is made out of, what it's composed of, by the light that it produces? Remember that the stars of our universe are very, very far away, and the ability to go and get a sample of the material of the star to bring it back home to figure out what the star is made out of is just something we can't do. So I'm going to show you how astronomers are able to determine the chemical composition or the makeup of a star or any other body simply by the light that it produces. So I want to start with a quote. And this is a quote from a scientist who lived in the middle part of the 19th century. His name was Auguste Comte. And in 1844, he was basically sharing the idea that we thought in the scientific community that we might never know what something is made out of, because as you can see in his quote, he says that humans will never determine the composition of the stars and planets because we will never physically visit them, and with no sample in hand, we'll be forever denied knowledge of their composition. His point is that if we want to know what a star is made out of, we have to go and get some of its material. And the reason why he felt that way is because in 1844, we were discovering that the stars were very, very far away. And of course, this is a full 100 years before the idea of putting rockets into space was something that was even close to a reality. So the idea was that we may never know what objects are made out of without the ability to travel these great distances and bring some of that material back to the Earth. But unbeknownst to him, a few years prior to 1844, there was actually a discovery of something that would lead to a solution to this problem. So let me show you this discovery. Now, it was in the year 1814 that an Austrian physicist by the name of Joseph von Fraunhofer had discovered something very, very interesting about our sun. Let me show you how he did this. So here is his portrait here. And you can see in his portrait, he is standing in front of an instrument. Here is a photograph of that instrument. It's a little hard to see in the portrait, and we'll talk more about that in a second. He's holding a prism in his hand, and Fraunhofer was somebody who specialized in producing instruments that were called optical instruments. These are instruments that are used to measure things optically. So magnifying glasses, microscopes, telescopes, and so forth. Now, the instrument that he's standing in front of is an instrument called a spectrometer. And we've spoken in a previous segment how the word meter means measure. So a spectrometer is an instrument that measures a spectrum. And if you remember, the word spectrum is the technical word that we use to describe the colors of the rainbow. If you recall, we mentioned it was called a visible spectrum. So a spectrometer is an instrument that allows us to examine the visible spectrum of colors with a great degree of magnification and close-up detail. Think of it as, it's like a microscope to use to examine a rainbow in up-close detail. And the way that it works is the light that you're looking at will enter this portion, and there's a slit. There's an opening that has a narrow slit. The light passes through the slit, and then it passes through the prism, turns into the visible spectrum or the rainbow. And then this portion right here is the equivalent of a microscope. Essentially, it allows you to see something with very close-up detail. And what Fraunhofer had discovered is when he takes his spectrometer and he aims it towards the sun, allowing sunlight to enter this part of the spectrometer, what he found was something quite astounding. You have to remember in the year 1814 there was no photography, so the best he was able to do was to produce a hand painting or like a watercolor of what he saw. And what you'll notice is the colors of the rainbow are shown here. So you have the red, orange, yellow, green, blue, violet. But what he discovered is that the spectrum of the sun, or the rainbow of the sun, is actually not continuous. You'll notice if you look very closely that there are dark lines where certain colors seem to be missing. And in some places the colored lines that are missing are very obvious, such as you'll notice the missing color right here, and in some places they're very faint. And altogether he discovers about a dozen dark places where colors should normally be. And even to this day, several hundred years later, we still call these dark places, we call these missing colors Fraunhofer lines in his honor. And what I want to show you is a more modern version of this, because this is the one that he produced almost 200 years ago. And I want to show you a modern day version of this very same phenomenon. So we're going to switch to an observatory. This is on Kitt Peak Observatory, which is owned by the United States. It's the National Observatory. And the telescope in this picture is called the McMath Pierce Solar Telescope. It is a telescope that's dedicated to continually look at the sun, so it's called a solar telescope. At the very top here is a mirror, and this mirror turns. So essentially all day long the mirror will turn so that the light from the sun will continuously reflect down this very long shaft. And inside of this room down here that's underneath the ground, inside of this chamber is a spectrometer, the instrument that's used to examine the spectrum of the sun. And this telescope has the ability to produce the world's largest rainbow. The rainbow that it produces is dozens of feet across, approaching 70 feet in size. You might think, why produce a rainbow that's 70 feet long? Well, the idea is the more details you hope to get from something will come from something that's very large. The bigger something is, the more you can zoom in on it to see very fine details. But the problem is when you have a rainbow that is 70 feet long, it's hard to put it all on one picture, because then you have to shrink it and you lose all the details. So what they do is they slice the rainbow into segments. So you notice here's a segment, here's a segment, here's a segment, and then they stack the segments. So the picture I'm about to show you is a sliced and stacked rainbow, or spectrum of the sun. And what you'll notice is you can see these long strips are those sliced segments, and the dark lines that run left to right you can ignore. That's just the gaps in between the segments. What I want you to notice are the vertical lines. So these dark vertical lines are called spectral lines. And altogether, the sun has more than 500 of these dark lines. Now remember, these are places where color should normally be, but color is missing for some reason. The color has been removed. And all throughout the spectrum of the sun, you can see lots and lots and lots of these dark lines where colors have been removed. Some of the lines are very, very broad. Some of them are very thin. Some of them are very dark. Some of them aren't so dark. And there's meaning to all of that. We'll eventually talk about some of that. But this is the entire spectrum of the sun showing all of its dark spectral lines. And by the way, this is the highest resolution image taken of the sun's rainbow, or its spectrum, that has ever been taken. Now, these dark lines were a mystery to Fraunhofer. He had no idea why it is that the sun produces these dark lines. He didn't know the cause, he didn't know the meaning of these lines, and in 1814 it was just a mystery. But what would eventually happen is other scientists would come along and make discoveries that would help to unravel this mystery. And what they would find is that the lines that you see, these dark lines that you see in the spectrum of the sun, are the sun's way of trying to tell us something about what the sun is made out of. And so what we'll find is the story behind how the scientists unraveled this mystery and were able to turn it into one of the most important discoveries that have ever happened all throughout science, but especially in astronomy. We're just about out of time, so we'll pick that up next time. I hope you'll join me.